Students, in this session we are going to see about how to measure the directivity of an antenna. So the directivity of an antenna is actually measured from the measurement of radiation pattern. We have seen already in the last session how to measure the radiation pattern of an antenna. Just look at the equation number 1. D equal to 41,253 divided by beam width in E plane and beam width in H plane. That is half hour beam width in E plane and H plane. So once if you know the half hour beam width of E plane and H plane, we can calculate the directivity of an antenna. This D, directivity of an antenna. So how to calculate the directivity of an antenna? See, the E plane and H plane beam width is to be calculated so that we can calculate D. So what is E plane? So E plane is nothing but it's a plane which contains electric field in the direction of maximum radiation. H plane is the plane which contains magnetic field in the direction of maximum radiation. So once if you have these two E plane pattern and H plane pattern, this E plane pattern, H plane pattern, by using the radiation pattern measurement, we can calculate the D value. So after calculating or after having the radiation pattern of E plane and H plane, you can measure the half hour beam width and half hour beam width of E plane and H plane so that we can have D value. Then similarly, this D value is the function of theta and pi. So that is the E is vary with respect to theta and pi. So D also vary with respect to theta and pi. So that let's look at the equation number 2. So D also varied with respect to theta and pi. See, D also vary with respect to D also vary with respect to theta. Theta means it is the elevation angle. Pi is nothing but is azimuthal angle in a spherical coordinate system. So this also varied with respect to theta and pi. That is, D is vary with respect to theta and pi. After variation, the d theta and d pi value is like equation number 3 and 4, where R Imax represent R Imax of theta and R Imax of pi is nothing but the maximum radiation intensity of theta component and pi component. And for calculating d theta and d pi, so we know to have the PR value and P radiated value in both theta direction and pi direction. So that we call it as PR theta and PR pi. When you evaluate this, the theta should takes the value, the integral value between 0 to pi, and pi takes the value 0 to 2 pi. So once if you know this values, I can able to find out the d theta and d pi value. Hence, in general, I can calculate the directivity of an antenna. The principal experimental setup for this directivity measurement is that the experimental setup which we have seen for a radiation pattern measurements. Then next we see the measurement of antenna radiation efficiency. So next one is the antenna efficiency measurement. So as we know, the radiation efficiency eta R is equal to power radiated divided by total power input, simply WR divided by WT. This WR is nothing but power radiated, and WT is a combination of, or the addition of, WR plus WL. WR is nothing but power radiated. WL represent this power from losses. So losses here may be a ohmic loss, maybe a I squared R loss, maybe a dielectric loss. So this also included in WL. So from that, so WR power, it is nothing but I squared R. Let's call it as a power. So here both, if I take I from this and from this, so finally I get cancelled. So finally I get eta R equal to RR divided by RR plus RL. It's nothing but radiation resistance divided by antenna resistance. This is one of the formula, and we know that the G naught, that is gain, equal to K into D is nothing but directivity. So here K equal to efficiency factor range between 0 to 1. Because why it is efficiency factor means, so assuming that there is a ideal situation, in this case there is no loss is present. So there is no loss is present means K value equal to 1, that is G naught equal to D, that is gain equal to D. So that I can define this K as a efficiency. So based on the K value, so the gain and directivity also get related. So when K value equal to 0, it seems that there is no gain. If it is 1, so simply the gain equal to directivity. So that I could say the K is considered as a efficiency factor. So efficiency equal to K equal to G naught by D, that is power gain divided by directivity. The another formula relating radiated power and the dissipation. Dissipation here is almost here WD we representing, here WL almost equal. So that based on that the input power, or the WT equal to the radiated power plus the dissipated power WD. From this I can calculate the WR equal to this one. From this eta R equal to, that is radiation efficiency, according to the formula, power radiated divided by total power input. So here the power radiated we calculated as WT minus WD. So that WT minus WD divided by here total power input. So that here total power WT. So from this you can have 1 minus WD divided by WT. So this is the 4 equations of calculating radiation efficiency. So out of this 4, so how to have experimental setup to measure this radiation efficiency. So see that the first equation, so it is a ratio of power radiated divided by total power input. So you can measure directly the power radiated and the total power. So once if you look at this is the transmitting antenna, this is the receiving antenna. So input power you can measure by using some power meters, and transmitted power, it is received by the antenna. You connect some detector here. Okay, so that detector detects the received power or power radiated. So that is a direct way you can find the total power input. So that from equation you can calculate. Similarly, look at the equation G naught equal to KD, this one, in G naught equal to KD. So we know already how to measure the gain. So gain measurement we discussed. So once if you know the gain value G naught, okay, you can find out the directivity. Okay, so once if you know the directivity, see that the efficiency eta R, K equal to G naught by D, right? So by using the G naught gain value then directivity, you can find out the radiation efficiency eta R. This is another way of calculating the radiation efficiency. Similarly, using equation 4 also you can calculate. Once if you know the dissipated power WD, okay, the input power you can calculate by direct method. So you have to calculate dissipated power by using connecting one power meter in the input section, you can find. So if you want to calculate the antenna radiation efficiency, either you can use the equation number 1, accordingly you can connect respective experimental setup, or you can use equation 3, accordingly you connect the experimental setup. The sense that you have to consider the experimental setup. For example, if you use equation 3, you have to consider the experimental setup for gain. First you have to calculate, then you calculate D, you can measure radiation efficiency. Similarly, the equation 4. So this is the way in which to calculate the radiation efficiency of an given antenna. Thank you students. Thank you all.